Hello guys, back with another video, and today as you can see it's another rectifier video. And what I'm going to be doing is the controlled rectifier, and I have done this in the past. I've done the half wave controlled rectifier. So today we're going to be doing the full wave. That means converting both your positive and negative half cycles into DC. And the particular converter which I'm looking at today is called the semi converter, because as you can see these two are thyristors, and in general when they say controlled rectifiers, it's implied that you use a SCR, a silicon controlled rectifier, or a thyristor. And that's what we're going to be doing today. So generally when they say fully controlled rectifier or a full wave converter, they mean 4 SCRs in this standard. Just replace your 4 diodes in the bridge rectifier with 4 thyristors, and that is what they call a full wave converter. And while that is good, that is generally unnecessary, when you're only looking at unidirectional power flow, which in, let's say, an example is a DC motor drive, right? Back in the old days, and maybe even today, some high power drives which are DC, they use this. And that is generally unidirectional. They don't want energy to feed back into the source, so we don't really need 4 thyristors over there. The 4 thyristor is a 4 quadrant operation. That means you can send power back as well. But if you're only looking at unidirectional power, you can use this configuration, which is sort of known as the semi converter, where you have 2 thyristors and you have 2 diodes. So basically the thyristors help you, decide the firing angle, which I'll just get into to revise it. If you want, you can go watch the older video on half wave controlled rectifiers. But just to give you a recap, I'll show that in a while. But here, if you use 2 thyristors, you can use that to control the firing angle in both positive and negative half cycle of AC, and you let the 2 diodes basically handle the freewheeling action. So these are uncontrolled. They will conduct as long as the voltage is greater, and you allow the voltage drop, so that will be allowed. But the thyristor again depends on when you give the gate pulse, and since this is AC, there will be natural commutation. You don't need any special commutation circuit here. So this is specifically called the symmetrical semiconverter because you have one thyristor and one diode on each leg. There's also the asymmetrical configuration where you have 2 thyristors in one leg and 2 diodes in the other leg, but I'm just going to be doing the symmetrical one. So let's go back into the firing angle, just a recap. So what you do is firing angle, or delay angle as they call it, that basically decides from when your SCR starts to conduct. So let's say you give a delay angle of 0 degrees, right? That means as soon as your positive half cycle starts, you give a pulse to the gate, and the SCR is it just needs a single pulse greater than its gate trigger voltage, and provided there's sufficient gate current, it turns on and it stays latched. That's what they call it, latched. And as long as the current stays above the latching current, it will continue. The switch will stay closed and it will allow your current flow. So it doesn't need continuous gate supply like a MOSFET or a BJT. So as let's say somewhere in this image, for example, they gave the gate at, let's say it looks something like 20-25 degrees. So let's say you give it here, it will conduct throughout, the start conducting from then on and continue till it goes to the zero crossing, because then of course your current is going to drop to zero in case of a standard resistive load, and then it's going to stay that until in the next negative half cycle again the same 180 degrees plus 20 degrees returns, and again it starts conducting. So this is how it will look. And let's say you give a very late angle, this is 90 degree, so this is somewhere like, somewhere like 150 degree, let's say. A very small part is going to, allow to be flowed. And yeah, so if you see, the average voltage is what your load reacts to is going to reduce as you increase your delay angle. So here the average voltage is almost your entire this part, just a small part is chopped off, whereas here you have a very small part. So the load will react to the average voltage, and that's how if you increase your delay angle, you can reduce the average voltage and per se the power which you are delivering to your load. So that's what this is. And of course I'm going to be they generally do this in the discrete way, they use 555 and a ramp generator, comparator, all that circuitry. But I'm going to be doing it in the microcontroller, the STM. So for the gate drive, we can use like a BJT kind of circuit where you use one of these pulse transformers. They are tiny circular transformers. I'll show it to you in a bit when I go to the hardware. And what they do is they just you can wire them like a relay, right? Like how you wire a microcontroller GPIO to a relay, same a BJT, NPN BJT, and a flyback diode. And on the secondary, basically, because this is just a 1:1 transformer, that's the turns ratio. So whatever pulse you give on the primary, that will sort of be replicated on the secondary. So you power your circuit with, let's say, something like 12 or 15 volts depending on the rating of this pulse transformer, and you give your pulse from the microcontroller at the base of the BJT, and on the collector basically that will replicate it, and on the secondary you will see the same high voltage pulse, because of course your microcontroller cannot directly drive the thyristor. That'll be a disaster. So you need this. Even provides isolation, so that's good too, since it's a transformer. So this one I'm going to be using the pulse transformer. And just to give you another idea here, just for simpler understanding, I said you give a single pulse, right? But in reality, often there are loads are inductive, right? Heavily inductive loads like a motor itself, as I said. So that may not turn on if you give a single pulse. So what they do is they give a stream of pulses, as they call it. This is unrelated, this for a digital circuit actually, but just to give you an idea, like how a clock looks, right? It has a certain amount of on time, it has off time. So you give these narrow pulses, let's say at 1 kilohertz is what I've done, and you give 100 kilohertz on time, 900 kilohertz off time. 900 microsecond off time. So 100 microsecond on time, 900 microsecond off time. So total 1 millisecond period. So if you give these small stream of pulses, somewhere along the line, the SCR will turn on, and even if it's a very inductive load, maybe towards the end of the pulses, but somewhere along the line, it will turn on. So this is more reliable rather than giving just one pulse. And another benefit is that these pulse transformers, right, they rely on the volt second balance. So if the average voltage, if there is some average voltage over the time across this, the core will saturate and then it will no longer work as a transformer. So that's why if you give these stream of pulses to, the volt second balance will remain maintained, and you can be sure that your transformer won't saturate, provided you don't give too much of a on time. So 100 microsecond is pretty small, and 900 microsecond anyway it's staying off, so that should be good. So generally they give these stream of pulses rather than a single pulse. A single pulse will work for a resistive load, but just for a general circuitry, it makes sense to use a stream of pulses. So that's the whole circuit. Here you can put your load across the DC part, and yeah, you give your AC to the midpoints of this full bridge. So that's the whole circuit. I'll just go into the code, I won't dwell too much on it. Basically what I've done is to select the firing angle, I'm using the encoder, digital encoder. So there's just the peripheral code for that. I've used a timer for that. The STM has an encoder mode, so you can use that. And just to we need, this has to be synchronized to the your AC, right? That means you need to know when the zero crossing has happened, and accordingly you can increase the delay angle. So for that you need to use some kind of synchronization, detecting when your positive and negative half cycle is. So like I did in my half wave control rectifier, where I had used the up to coupler circuit, you can use that too, but today I've just used like a ADC sort of circuit where I'm converting my 12 volt step down mains, which I'm using from the transformer, to basically convert that to fit the ADC range of the microcontroller, and then via code detecting the zero crossing. So this is actually quite unnecessary for this, you don't really need that, but I just had that part of the circuit ready, so I went ahead with it. So you basically just do that, you detect the zero crossing, you use a timer to delay depending on how many millisecond you delay it depending on your firing angle, and then basically you start the pulse stream and you stop it at the next zero crossing. So that's the whole idea of it. So that's what's going on in this code. That's basically, checking how much the encoder has moved. And I have given a lookup table. So basically, this is translates to microseconds. So basically, starting is zero, basically 0 second microsecond delay, which means immediately, and after that 500 microsecond, 1000 microsecond, which is 1 millisecond, and so on. So the delay angle increases. So as I move my encoder, it will basically move ahead in this lookup table. And accordingly, in this ISR, if I go down to the interrupt service routine, it will, fill that value into the register, and accordingly it will be sent to the pulse transformer via the BJT. And yeah, it will go to the SCR, and the SCR will get gated at that particular delay angle. And you'll get the average load voltage across the load. So that's the whole code. And if you want to learn more, there are, plenty of videos on this, understanding how gating works. And you can even run a simulation. I haven't really run a simulation for this, since it's pretty simple, we don't really need one. But yeah, that was the whole part of it. And I'll just go into the hardware now, and let's see some waveforms. Okay, so this is, we have the hardware circuit, and the same STM32 board. It's proving to be a very good, companion. It's very nice. It's good to code and understand too, and it has a lot of peripherals. So yeah, this is the STM board. And this breadboard, this small breadboard, basically houses the AC detection part of it. What I said, converting your step down AC. This is my transformer, and this basically gives sort of like a 12 volt RMS output. So converting that to fit your ADC is range. So that's the circuitry for that, with the op amp and all. So I won't go too much into that, but yeah, that's the circuit for that. And this breadboard houses the actual power circuit. So through the microcontroller reads this AC signal, where you can use your optocoupler if you want. That's much simpler for this case. And that basically reads it, and the output of it goes here, the pulse stream, to the BJT. I have two BJTs. Since I'm doing the semi converter, we need two pulse transformers and two driver circuits. So two identical driver stages, one BC547, other BC547, and those are the two flyback diodes and gate resistors, and those basically go to the pulse transformers. So these are the pulse transformers, as I said, 1:1, and they look circular like this. So I have two of them over here. And after that, it goes to our SCRs here. These are the two SCRs, TY and 612s, standard TO220 SCRs, and two diodes, so 407 diodes, standard bridge rectifier diodes, which you use very commonly. And here is the load. I'm just using a 50 ohm 5 watt power resistive load over here. So let's just turn this whole circuit on. And of course, I forgot to mention, you this but depending on your SER, you need a sufficient gate trigger voltage and gate trigger current. So I'm powering it, the driver, using this my bench supply. So I've set it to around 12.5 volts. So yeah, that should be good. And now if we look at the waveform, you can see this is roughly, I haven't moved the encoder yet, so this is roughly at 0 trigger angle. So I can see there's a bit of jitter, but if you ignore that, it's roughly acting like a normal uncontrolled rectifier. And we have a average voltage of roughly 9.1 volt, as I can see. So now I'll basically just move the encoder over here, and you will see how the delay angle increases. So I increased it a bit. I'm moving it over here, and you can see, even though it's sort of looking like it's dancing, but if I just stop this waveform for you, you can see a part of the sine has got chopped off, and your average voltage reduced to around 8 volts. So let's continue increasing the delay angle, and thereby decreasing the average voltage. So I decreased it a bit more, and now you can see if I stop it, you have a small part of the sine, and only around 3.72 volts average. And again, I'm doing multiple steps with this encoder. You can fit that's the beauty of the encoder. You can basically choose how much our delay angle increments depend in the code. I just used a lookup table. So yeah, that's what that was for. And you can see that both half cycles are changing, and that's why it's the full wave converter. And I'll increase it further. Now you can see a very small part is remaining, and you have like roughly around just 500 600 millivolt, so it's a very small voltage which is remaining. And if I continue increasing it at one point, basically, which is roughly around here, you get 0 volts, which is practically translates to, even though this part is randomly appearing, it's practically 0 volts. Now if I go back, it wraps around the logic of the STM. So since this is in encoder mode, so you can see we are back to our normal uncontrolled part of it. So yeah, that was the whole controlled rectifier. I can show it to you again. By moving this clockwise, we can increase the delay angle and thereby decrease the average voltage, if you keep your eye on that average voltage below. And yeah, maybe my trigger is acting up a bit, that's why it's moving a lot. But nevertheless, we can see it's working properly. I can move it in the other direction too, and now we're back to the uncontrolled rectifier. So if you give your delay angle to be, something like 90 degree, I can move it to roughly 90 degree here. This is somewhat how your 90 degree delay angle will look. Yeah, something like this. So yeah, that is that. And the other one, now just to show you how it works, what I can do is, instead of using a power resistive load, I can use a motor load, a small DC motor, and you can see the speed change in real time, and that's better to look at rather than a waveform. So yeah, I'll just switch the load. Okay guys, so now I've switched out the resistive load for the motor, and this is just a small tiny 12 volt motor. And you saw at the 0 degree firing angle we had a maximum of average voltage of around 9 volts, so that is going to be our reference point for maximum speed. And as you increase the delay angle, let's say 10, 20, 30, and then 90 and beyond, the speed is going to gradually reduce. So right now I have the supply and everything on, so I'll just give it one turn. Right now it's sitting at like 90 180 degrees, so it's off. So if I just give one turn over here, it started rotating, and this is roughly full speed. And now if I start increasing it, I increase the turning it slowly, you can see that it will slowly start to slow down. So I'll just give it a few clicks, and roughly now we're at half speed. And even though you can't really see it in the camera, it has slowed down over here if I see it with my own eyes. And let's give it a few more ticks on the encoder to slow it down further. And I gave around 3 ticks, and now you can see clearly on the camera the rotor has slowed down because the average voltage has reduced. Now giving it 1 or 2 more ticks, now it has reduced quite a bit. If I just give it 1 tick, now you can see it's visibly very slow. And if I just give it 1 tick more, now where it has stopped completely, because basically it has reached the 180 degree delay angle. And if I go back in the other direction anti-clockwise, we'll go back to the preponing our delay angle and going back to the fast speed. So I'll continue increasing it back to the maximum. As you can see, it has sped up again. And now we're back in the other direction to 180 degrees. So yeah, this was the whole controlled rectifier. And if I had a more powerful motor, you could see it better. But just for understanding, I hope you got how you increase the delay angle and your motor slows down. So this is somewhat like PWM in the sense that the average voltage, what you apply to your motor is what it sees, and accordingly adjusts its speed. So currently I'm doing it open loop. Later, if you want, maybe in the old style how they used to do closed loop control, you can do that on the motor. That will be interesting to see if somebody does that. But yeah, that was the whole closed loop, open loop motor control using our fully controlled converter or semi converter. And yeah, I hope you learned a thing or two. This was a pending project from a very long time. It was sort of stalled, but yeah, I recovered it, and yeah, it seems to be working well. So yeah, thank you for this watching, and stay tuned for future videos. Bye.